Good morning, ladies and gentlemen. This is Ben Kieser with Applied Flow Technology, and I hope that all of you are doing very well and having a very fine week so far, and that everything is going great. Anyway, thank you for joining me on the webinar today. I'm very excited to discuss the content with you all, and today we're talking about transient analysis. Now, if you want to go into greater detail and be able to refer to this type of content, later down the road, 6 months from now, whatever, you can certainly watch the recording of the webinar, because this webinar is being recorded, and as usual, you'll be sent a link so you can watch the recording at your leisure. You don't have to ask for it. We'll just send it to you later this week. And then secondly, is that this is actually also covered in a blog article that I wrote a couple of months ago. So if you go to our website, aft.com, under the Learning Center and then Tips and Tricks, this is where you can find all of our blog articles that we've written in the past. And that way you can get some really solid guidance on how to use our software in more effective and efficient ways. And we are constantly writing articles for this. So definitely be sure to check this page out and keep an eye on it periodically. We usually will put out at least 1 or 2 blogs a month. And so this is a blog that I wrote back in July, What is Transient Analysis? And so I'm going to be covering the examples live. That way it's a little bit easier than having to read it. So, but if you want to refer to it later, that's where you can find that information. All right. So with getting into things here, if you go to our AFT software overview under the products menu, this is where you can find all of our various applications: AFT Fathom, AFT Arrow, AFT Impulse, and AFT Extreme. So today I'm going to go over when would you use AFT Fathom with the extended time simulation module for doing transient modeling versus when you would use AFT Impulse for transient modeling right here. And so if you're doing a transient analysis, either tool might apply to your specific application. Both might apply to your specific application. And so we're going to go over the details of each of those in the webinar today. So let's go ahead and get into it. I'm going to start off by talking about AFT Fathom using the extended time simulation module first. So here's our AFT Fathom model, and it's a very simple system. I have a reservoir with a pump, and I'm pumping up to 3 different reservoirs at higher elevations. Now, how do you turn on the extended time simulation module with AFT Fathom if you want to do transient modeling? Well, if you click on the button that says add-on modules, this is where you can turn on the add-on modules. As you can see here, I already turned on XTS, and as you can see, the box is checked. So once the software finds that you have a license available of the XTS module, it'll simply stay checked. So once you see that it stays checked, that means you've turned it on, you're good to go, and you can use it. So I am doing a simulation where I'm pumping water up to these 3 discharge reservoirs. And with this being a transient analysis, I want to know how long does it take to fill up each reservoir, and how much does the supply tank drain, and when do each of these valves close in order to prevent their associated tanks from overfilling. So that's what we're trying to figure out today. And the first thing that you're going to notice when you turn on the extended time simulation module, you're going to love this. The reservoir window changes. And so if you're used to looking at this, you don't have very many options until you turn on XTS. You can then model finite open tanks and closed tanks. And that gives you a really big advantage because you can model the actual geometry of your tanks, and you would be able to see how the liquid level changes over time. So that's a really powerful benefit. And in order to do that, that's where you're going to need to use the XTS module. So you can do some really sophisticated stuff with this. You can also have, you know, another reservoir upstream where, you know, maybe this is a reservoir at the top of the hill and you're draining down into the supply tank here. And so we can actually do when you're using the XTS module, we will do a mass balance around this in order to determine what the accumulation is inside the tank. And so that's a big benefit with using XTS. If you're just using standard Fathom for steady state, then it's going to be limited to using only the infinite reservoir option, where all you're doing is specifying a constant liquid surface elevation, a surface pressure that's acting on the liquid surface, as well as where your pipe is connected at. And your liquid level stays the same until you change it manually in this field right here. All right, so that's one of the things that we have going on with XTS is all of our tanks are finite open tanks. So they will fill up and drain over time accordingly. And when you specify a tank height, Fathom will give you warning messages if you start to spill over your top of the tank, which you definitely do not want to have. So that's important to enter that information there. Each of my tanks also has a different diameter. So you have a 20-foot tank, a 10-foot tank, and a 30-foot tank. Those are the diameters there. And then the tank heights are also different. So the medium diameter tank here has the highest liquid height, or the highest tank height. And then we have 20 foot and 10 feet. That's not a negative sign right here. This is just a dash. And so don't think I'm saying negative values right there. I'm not. All right. So here's our pump. And our pump is operating on its curve during the entire transient simulation. And so initially, the pump is going to operate somewhere on this curve, and then it will move back and forth depending on what the circumstances are. All right, now let's take a look at the valves. This is how I want to prevent overfilling from happening. So in valve A, when I open this guy up, he is using a handbook loss model for the K factor. And when we look at the transient tab, this is where I'm going to close the valve. So there's a lot of different ways that you can model transients in the software. There's 4 different ways, and you can get really sophisticated with them. I'm going to do a very simple single event transient right here. So whenever you're working with an event type of transient, that means that you have to have criteria that is met in order to cause this transient profile to activate. So here we're closing the valve in 5 seconds linearly. -1 represents a closed valve in our software in terms of K factors. So we're closing the valve in 5 seconds. What causes the valve to start closing? Well, it's a single event transient where we have specified that if the reservoir liquid height gets to be greater than or equal to 28 feet in J4, which is this tank right here, that is when this valve transient is going to activate. So it's worth noting here that if this criteria is never met, in that case, this valve will never close. So if we never get that liquid height, that valve is going to just keep staying open until the criteria is met. One question that I just had is, can you turn off the flow paths and see how it impacts the other flows and pressures to the other two flow paths? And the answer is yes. And you're actually going to see that in AFT Impulse with other scenarios, because that will actually be necessary to do the AFT Impulse analysis for a waterhammer situation. All right, so we've got valve A defined, valve B. They're all going to close in 5 seconds, and they all have their own liquid heights that they're going to be closing based off of. So this is 18 feet for J5. And then finally, we have this valve right here. This is going to close within 5 seconds when this supply tank here with the largest diameter gets to be greater than or equal to 9 feet for the liquid tank level. All right. So this could be a fairly long process to fill up these tanks. These tanks are very, very large. And so when you're trying to figure out how long it takes to fill these tanks, you know, and you're trying to determine how long should you run your simulation for, well, maybe start, 30 minutes, see how long it takes. If nothing happens very much in that first 30 minutes, then try an hour, then maybe 2, etc. So I've already gone through that process, and I've determined that, or I found out that what I need to do is I need to run a 4-hour transient simulation. So let's talk about this real quick. Let me cancel out of there and show you where you can find it. So let's see, make sure this is all good. Okay. All right. So when you go to the analysis menu, under the transient control, this is where you can specify how long it takes for your simulation to run. So here, I'm going to do a 4-hour transient simulation. That's 240 minutes. You can change your units here with the drop-down menu. So what I'm doing is I'm doing my simulation time in terms of minutes, but then for my time step, I'm doing a time step every 30 seconds, okay? So let's draw a little timeline here. So here's our timeline, and this is time 0, okay? So there's time 0, and here is 240 minutes. Okay? I'm doing 30-second time steps. So I'm going to just, this is not to scale with drawing this picture. So let's just pretend here. I'm going to use a different color actually for the time steps. So here we have, this will be 30 seconds, 1 minute, and then 1.5 minutes, 2 minutes, 2.5 minutes, 3 minutes, etc. And again, this is not to scale. Pretend that this distancing is all even. This is just my bad drawing skills. What I am trying to illustrate here is when I define the valve closure that happens in 5 seconds. Okay, so let's do a different color here. So let's say that this green is 5 seconds right there. Okay, so I can type in 5. All right. As the transient simulation period goes forward, there's 5 seconds, 10, 15, 20, 25, and then here's 30. Okay. So look at what has happened here is that in this time frame, within the first time step right here at 30 seconds, this valve has closed in 5 seconds, and it has stayed closed for 25 seconds. What happens when a valve closes? Well, you're going to have a sudden pressure surge that is going to be reflected throughout the system. AFT Fathom with the XTS module is not going to capture that behavior, okay? It's not going to account for the wave speed of the fluid. It's not going to show you how your pressure waves are propagating back and forth throughout the system very, very quickly. It's capturing fairly slow changes in the system. So here, if we are specifying a 30-second time step, and if things are changing relatively slowly, then maybe from one time step to another, these might be all at a steady state operation. So let's say that we froze the system at this particular time step. If we freeze the system and we don't change anything else, then we're going to see the same values going forward, all right? Because the key thing with the AFT Fathom XTS module is every single time step represents a steady state operation. Give me 1 second. All right, so with every time step being a steady state operation, there's a lot that can happen in a waterhammer situation, and that's where we would use AFT Impulse. All right. So back to the flow model here. I'm doing a 240-minute or 4-hour runtime, and I have 480 time steps, okay? The transient solver is very simplified. You can do either a forward difference or a central difference for the transient calculations, and we're going to go ahead and run the simulation. So let me save this here. It's always good to save. Let me give you a little tip, a couple of tips here. Automatic save, where do you find that? If you go to the tools menu and then user options, this is where you can configure all your different preferences. And so down here near the bottom at backup settings, this is where you can specify backup files to be created and how often you want to automatically save the model. So what are backup files? Every time that you save your model, or if you're using automatic save, every time it's saved, Fathom is going to create a backup file. It's going to have an extension BAKF for Fathom -001, okay? And it's going to create up to 3. So you'll have BAKF-002 and then -003. The 001 backup file is your most recent backup file. So if you ever had a situation where unfortunately your model file gets to become corrupted, look for the file that's in the same folder as your model and look for the one that has the same file name, but then the different extension of BAKF-001. Simply change the extension to FTH and then run Fathom, go to File, Open, browse to the file that you just renamed, open it, and that will recover your most recent backup file. So that is really important to know. And then you can turn on automatic save. I recommend not doing every single minute. I would keep it minimum every 5 to 10 minutes, because we're all really busy. You're working on a model, you're doing a whole bunch of things that you don't want to keep in the model, and you get up and you go into a quick 5-minute meeting, and that 5-minute meeting turns into 2 hours. Well, this is already saved several times, and it's going to save all those changes. So if you went to any of those backup files, it's not going to go back to the state that it was before. So this is where I recommend doing every 5 or 10 minutes. If I'm troubleshooting model, I never use automatic save because I'm messing around with all sorts of things when I'm troubleshooting. But if I was doing a consulting project, working on a model, building a system, then I would use the automatic save. So that's where you can find that. And then one other tip, don't ever work on, run, or save model files over a network server path. Never do that. that is a major cause for file corruption, because if you have a very, very slight hiccup in connection to your network server, then while you're saving, that can cause file corruption right there as well. So I always recommend that you only work on, run, and save model files locally on your own computer, like your desktop or something. Then once you're done, close the software and then move your model back up to the server. If you adopt that practice, you're going to avoid file corruption issues very, very well. All right, back to the transient simulation here. Let's run it. I guess I should have talked about that while this was running, but I wouldn't have been able to show you the where automatic save was. All right. One thing that I want you to think about when you're working with the AFT Fathom XTS module is long-term transient simulation, okay? You're going to be doing simulations where you're modeling, several minutes, hours, maybe even days. It's meant to capture the dynamics of your system over long periods of time. And so that's where you'll get a really good picture of how long it takes your tanks to fill and drain over time. You can also do things where you specify, let's pretend that this is a different type of a junction. If we were to do a controlled pump flow rate where it's starting at 500 gallons per minute, let's say that you have data where you know how the flow changes over time. You can define that as flow demand versus time data, and then you can see how your system will respond to that. You can do that for your pump or control valves or regular valves that maybe you know how their position changes over time, or a simple assigned flow junction where you have a flow demand somewhere and you're using that as a boundary junction. Well, if you specify that flow demand with a assigned flow junction, you can vary the flow rate over time, and then you can see how your whole system responds to it. Those are all excellent applications for the AFT Fathom XTS module when you're looking at things over long periods of time. All right, now I'm going to collapse my quick access panel for right now, and let's take a look at things here, kind of a high level, and then we'll dig down deeper into the results a little bit. So this is the output window that stores all of your results in a tabular format. We are all used to, the first couple of tabs, the pipe tab or the piping results section, junction section. But when you're dealing with a transient analysis, there's a few more things to pay attention to. Event messages. Now we have a pump summary and a pump transient. Valve summary and valve transient, reservoir summary and reservoir transient. Okay, we also have, so let's talk about that really quick. Event messages, what are these? I like to look at event messages by time first, because this is going to tell you what events are happening. This answers the question of when are those valves closing. So actually in my system, valve B, the one in the middle, that valve closes first, followed by valve C, the one on the far right, in 113.5 minutes. And then the first valve in the flow path, valve A, that closes in 187 minutes. So this tells us what events are occurring in a chronological order. Now let's say that you had a chattery check valve that is opening and closing several hundred times. Well, if that's your situation where it's opening and closing several hundred times, you might want to evaluate a particular junction's event messages. That's where you can look at event messages by junction. This way it would show you all the events first associated with junction J8, and then all the events with J9, etc. So if you have hundreds or thousands of events going on, it can also be helpful to sort by junction number in that regard. So that's what the event messages tell you. This is a really good place to start when you start trying to figure out what's going on with your results. in order to keep things a bit more, well, let me talk about the middle and the bottom section first, okay? These are your results in the pipes. So if I collapse this, these are my pipe results. Now, one thing to notice here is that these are the results at time 0. How do you move forward to different time steps? Well, that's where we have this time slider down at the bottom. So if you click on the single arrow to the right, that goes forward one time step at a time. So I can move forward and back. I can move all the way to the end. I can move all the way to the beginning, etc. So that is how you can see your results for all of your pipes one time step at a time. There's another way to look at this, and this is the transient tab. So here, we're still looking at all of the pipes results, but every single time step is captured in this expansion box. So if you want to see everything that's happening, or if you want to see all the results of pipe 1 over time, you can expand that. And you can see here half a minute, 1 minute, 1.5 minutes, 2 minutes, etc. And so this expansion gives you the transient results for pipe 1 at all time steps. If you want to look at the flow rate, you can right click in a column and you can do a quick graph. And so this gives you a picture of how the flow rate is changing in that particular pipe over time. So this is pipe 1, pipe 2, pipe 7, etc. So those are two different ways to look at your pipe results. The junction results at the bottom, same idea. Now, we have junction results at the bottom and then also junction results at the top. How are those two sections different from each other? Well, the junction results at the bottom, these are common junction results that apply generally to all junctions. So these are very simple. Inlet pressure, outlet pressure, flow rate, K factor, etc. If you want to look for the best efficiency point of a pump or a valve CV for a valve, those two parameters don't mean anything for a reservoir or a branch junction. And so for junction specific results, you're not going to look at the tabs down here. You're going to look at the tabs on the top, the summary and the pump transient tabs. Okay, so if you were to open up the output control window, which is this button right here, this is broken up into many different buttons. So pipes will give you results in the pipe section. And then the junction results, these are general junction results. These results right here are given down in the bottom junction section, common junction results. Now we also have a junction transient tab. That's very similar to how we had the pipe transient tab. And so you can specify which junction transient parameters that you want to see down below in this tab right here. Now these are component specific tabs right here that appear in the general section at the top. So if you want to look at pump specific results, you're going to click on the pumps button, and this is where you can add additional parameters to the list, and then these parameters will be shown in the pump summary window. Okay, and the pump summary, that's just going to show you one time step. You can use the slider down below to move forward time steps, but only one at a time. Next, the pump transient is going to give you the output results that you can see in the pump transient tab right here. And then the valves button gives you the valve summary, valve transient gives you valve transient, so on and so forth. All right, so I'll hide that. All right, let's take a look at how the pump is changing over time. So again, if I click on the pump summary, this is going to show you the pump results one time step at a time. All right, if I go to the pump transient tab, this is where I can see all my pump specific results over time. So I just like to go in here and quick graph these. So if I right click, I can do a quick graph of the flow. So that's how the pump flow changes over time. And as each valve closes at different times, you can see how the flow rate drops. You can also see how the pump head rise changes over time. And notice how when the last valve closes, this is where we're operating at the shutoff head. So that's the pump shutoff value when you have no flow through the pump. You can track the efficiency over time. There we go. So there's the efficiency over time. It stays at 100% because I didn't do a, oh, that's the speed. I'm sorry. Oh, okay. So if it has not applicable, it's not going to show you a graph for that. That's because once we get down to zero flow, the efficiency data goes away. So that's why we have not applicable for some parameters. You can also monitor your BEP proximity. This column is really important because as you're changing your system, you want to make sure you're operating with good proximity to the BEP. Now, here's the thing. It's not graphing these with the quick graph, but you can get a lot more use in the graph results. So let's do that. Let's go to the graph results tab here. When I go to the graph results tab, I've already created several graphs here that I can choose from, but let's do it from the start. So if I go to the transient tab, what I would need to do first is pick what type of a graph I want to look at. So I can do general junction results. So these are common junction parameters. I can do pipe results, pump results, reservoir, etc. So let's start off with the pumps, okay, or pump, because there's only one. You would check the box for how many junctions you want to plot. I'm not going to do speed because I know it stays the same. So I'm going to do volumetric flow rate. And then I'm also going to do head rise. Now for head rise, on the second parameter here, I'm going to indent it to the right. That's going to make it a secondary y-axis for this graph. Next, I'm going to show the percent of BEP, and then I'm going to show the MPSH margin as a ratio. And there we go. So this gives you a really good picture of what's going on during the transient. So here I have flow rate through the pump and head rise. So you can see how the flow drops over time. And then you can see how as the flow rate decreases, your pump head is increasing. That's basically where you're simply riding back on your pump curve. And then you can see here your BEP proximity. So when that first valve closes, your BEP proximity drops to about 80%. Not bad. When your second valve closes, you're down to about 70 to 75%. That's where you're at right before the valve closes. And then once that second valve closes, look at where you're at right here, 45% of the BEP. And look how long it operates here. Right now you can see this is in terms of seconds. Let me change this to minutes. So here I'm at 114 minutes that I start operating at 45% of the BEP. And then in 187 minutes, that's when I'm down to 31%. So in about, in just a little over an hour, you're operating between 45% and 30% of the BEP. That's something that you're really going to want to pay attention to because this can start causing reliability problems with your pumps. since you're operating so far away from BEP. This is really important to pay attention to, and this is how easy it is to get with looking at the graphs here. All right, and then at the bottom we have our MPSH margin. So you can see how the margin thankfully increases over time as the valves close, and then everything drops off when we are at zero flow. So that's the pump right there. And someone asked a question, you can't click on a pump and just graph it. Well, not in Fathom, because it's really easy to do it just right here. It's a bit more basic. In Impulse, there's a lot more enhanced functionality with graphing, because in Impulse, you're always going to be graphing things. And it is possible to generate graphs from junctions in Impulse, and I'll show you that here in a little bit. All right, let's take a look at some other results that I was looking at here. One of the things that I looked at is my reservoir liquid height versus time. And so this is showing what's going on in 250 minutes. So this top curve, this is my supply tank. So you can see how the supply tank drains over time. And then each of these three curves are the discharge tank liquid levels. And so you can see here the time at which this liquid tank is at when the first valve closes, the second valve closes, and the third valve closes. Now, when you pay close attention to this, you see a slope change in each of the graphs when the valves close. That's because additional flow is going to the remaining tanks that are still open. So that's something that you can get out of that information there. This is the same graph, but just at, I ended it at 200 minutes. Now, this is something that we're going to start comparing with AFT Impulse. Pressure at the valve inlets. So when you look at the pressure at the valve inlets, I'm doing this in terms of pipes, okay? So the outlet of pipe 3, outlet of pipe 5, and the outlet of pipe 6, this is where the valves are located. So here we have pipe 3 at the outlet, 5 at the outlet, and 6 at the outlet. Those are my valve inlet pressures. And when the valves close, I'm going to compare the pressure increase that I see here with Impulse. And the whole question is this correct? Well, let's break it down a little bit. So let's just look at the, let's see, valve B, that one closes first. So here at valve B, if I turn on my crosshair, my pressure is at 189 PSI, and it jumps up to 197. So that's about a 6 PSI increase when the first valve closes. And then when the second valve closes, I go from 198 to about 204. So those are very small increases in pressure. And then we can see what the pressure is once we are deadheaded. And then we can also look at the valve A. So here we're at 191 and we go up to 197. And then when valve A closes, we're at 198 up to 203. So these are not very high pressures that we're seeing when the valves close. This is the biggest one. From valve C, we go from 196 up to 204. So that's a 10 PSI increase. So I want you to remember that we were seeing about a 5 to 10 PSI increase at the valve inlets when the valves closed from what AFT Fathom XTS told you. And then we'll compare that to Impulse. All right, a few other things. This is plotted the liquid surface elevation. So this is accounting for the liquid level in the tank as well as the actual elevation of the tank. And then here's our pump flow head and our DP. So I have suction pressure and discharge pressure. So we can see the pump DP over time. So those are different parameters that we can look at. All right. Now, remember these times that the valves closed: 32 minutes, 113.5 minutes, and 187.5 minutes. Remember, the valve here closes within 5 seconds, okay? Because we were using a 30-second time step in Fathom XTS, this closure is considered instantaneous. So when we look at this in AFT Impulse, that's not necessarily going to be instantaneous anymore. We need to see what the response is going to be immediately at the valve closure. So that's where we need to do a waterhammer analysis so we can capture the rapid propagation of pressure waves throughout the system. So in Impulse, I'm actually going to be doing a number of different scenarios. My first scenario is going to be modeling all of these valves being open, and I want to see what happens when the first valve closes. So this is where it's really important to track the liquid levels and the liquid surface elevations properly, because at the time frame that this valve closes, I need to know what the liquid surface level is in all of my tanks. Well, this is really easy to get from the AFT Fathom XTS simulation right here. So this is the liquid surface elevation versus time. I already copied the XY data and I plotted it in a spreadsheet. So here is all my liquid surface elevation data. This is supply reservoir and then my 3 discharge reservoirs. And what I did was, down the list, I noted the times that the valves closed. So this is when valve B closes, and then we have the valve A close. Oops. We have the valve A closure and the valve B closure. And then all the way at the top, this is where I simply summarized the data. So I have valve B closure, that's that time frame. This is the time step at which valve A closes, and then this is the time step at which valve C closes. So Impulse is going to model immediately what happens at each of these 3 time steps, okay? So I'm going to need to do at least 3 separate simulations to determine what's happening with the valve closures. So let me go ahead and jump into my AFT Impulse model. When you bring in a Fathom model into Impulse, it's really easy. All you do is you go to File, Open, hang on. So you go to File, Open, browse to the folder where your Fathom model is located, change the file type to all. And so here, this is where you can select your Fathom model and then just click Open, and that'll bring it right in. Now, I'm not going to do that here. I already did that. And so this is basically what I had in Fathom. So in Fathom, these were the scenarios that I had. And then in Impulse, these are the new scenarios that I created. So I'm going to focus on these scenarios right here. So here's the valve B closure scenario. Valve B closes at 32 minutes into the XTS simulation. That's when the valve closes. Now this has a lot of output data that it's trying to go through, so it's actually unarchiving the results that I already got. Okay, so this looks very similar to Fathom. Couple of differences here. When you're dealing with AFT Impulse, these are 2 additional checklist items that you have to complete. Pipe sectioning dictates how your pipes are broken up into bits in order to do the method of characteristics calculations. I'm not going to do a big discussion on this. I'm going to refer you to a video tutorial on pipe sectioning. So if you go to our website, aft.com, under the Learning Center, and then video tutorials, if you do a keyword search for sectioning, this is where you can watch the demonstration on pipe sectioning. This is a really, really important video to watch and understand how sectioning is dealt with in Impulse. Now, this was last updated for AFT Impulse version 6. We are currently at version 8. The sectioning method and process is exactly the same in Impulse 6 as it is in Impulse 8. So you can watch that video and you'll know exactly what needs to be done. Now, the transient control, this is a little bit different because, well, same thing with the time step. In Fathom XTS, you could specify what the time step is. I set that as 30 seconds. That's not the case in Impulse. In Impulse, your time step is determined based upon the pipe sectioning. Once your pipes are sectioned, then your time step is done. And look at this, it's really small, 3 milliseconds, okay? So when you think of waterhammer modeling with AFT Impulse, I want you to think short-term transient simulation. That's because these waterhammer events are happening in very, very short time frames because the wave speed of your fluid is typically on the order of several thousand feet per second. Look at that. It's all around 4,200 to 4,400 feet per second in this model. So those pressure waves are going to communicate themselves through the system very, very quickly. So that's where we need very small time steps in order to capture what's happening. And so this is using 3 milliseconds for the time step. And then once the time step is determined, what you would specify is your stop time, just like you did before. But here, I'm not going to do a 240-minute long runtime. I want to see what happens immediately after the valve closes. So when my valve closes at 32 minutes, remember the valve closes at 5 seconds. I might want to see what happens in the first 30 seconds to 60 seconds of simulation time when that valve closes, because is the pressure and velocity waves going to fully dampen out within that time frame? So if I'm talking Fathom XTS, here's a given time step at times, let me reset. So if this is Fathom XTS, where this is at 32 minutes, and then I have 32.5 minutes, and then I have 33 minutes, this is 60 seconds of runtime. And in XTS, we have no idea what's going on within this time frame or this time frame. But in Impulse, there could be a lot going on in this 60-second period that's not going to be captured in the XTS module. So here, you're going to be doing much, much shorter simulation periods. All right, so I've got my stop time of 90 seconds. I'm saving the results for all intermediate pipe stations with the sectioning. I already ran my model. And so I basically took these values from the spreadsheet and I specified the liquid surface elevation at that time, at 32 minutes. Same thing with all my discharge reservoirs. And then my pump is just operating on its curve. I still have flow through valves A and C, so I don't need to do anything with those. Those valves are just open where they are. This valve right here is the one that closes, and the time zero in my start time of the simulation, this equates to basically 32 minutes from the Fathom XTS simulation. So I'm assuming that this time zero corresponds with 32 minutes, I'm doing a time transient. I'm not doing any event-based stuff because I already know that my valve is going to close. So I don't have to set up criteria for it. So this is the same type of valve closure, 5 seconds, and I'm going to see if this causes a difference in results in Impulse than what we saw in the XTS module. So I already have results. Let's take a look at the output window. With the output window, the tabular format for results is not as beneficial. I almost never look at the junction section because these are only showing you the results for the steady state situation right before the transient begins. So I usually immediately collapse that. What I do look at is the warnings. So here, this is just telling me that once my valve is closed, it stayed closed to the rest of the transient simulation. All this is doing is telling me that in order to just really be clear what's going on, I should say 90 seconds right here like this. And this would be a very clear way to very, carefully show that once the valve is closed, it stays closed to the whole remaining simulation. But you don't have to do that. You don't have to enter that third data point. You can leave that blank like how I did. And so this message is simply telling you that it's assuming that your valve position stays at the last data point for the rest of the analysis. That's not a big deal. This is telling you that you have cavitation going on. And so in pipe 8, station 0, we have some significant levels of cavitation. Where is that occurring? Well, if I go to my workspace, I can see here that this is pipe 8, and that is downstream of the valve. Excuse me. And so cavitation is definitely something that we want to look at, but today, for the sake of time, I don't care about what's going on downstream of the valves once they're closed. It is important to pay attention to, but for the webinar, I'm only focused on what's going on upstream of the valves. Now, while this valve and this valve are still open, I am concerned with what's going on, but only when those valves are open, because the wave will pass through those valves and reflect off of these discharge reservoirs, and then the wave will come back and it'll interact with all the other pressure waves in the system. All right, and so that's my warnings. And then here you can see what your maximum pressures are. And let's go to the graphs. So let me collapse my checklist. All right, let's take a look at and see what's happening for the pressure and the vapor volume at valve B. So I already created this graph. Let's see, while that is loading, somebody else asked, in case of a sudden valve closure, does this still apply, or would a smaller time step be needed? I'm not really sure what you're talking about there. I mean, in Fathom XTS, your time steps are going to be longer. In the waterhammer analysis with the AFT Impulse, your time steps will be exponentially shorter. Again, remember, my time step in Fathom was 30 seconds. My time step in Impulse was 3 milliseconds. Now, if you are asking for Fathom XTS, can you do a smaller time step? Instead of doing 30 seconds, could you do a 5-second time step in Fathom XTS? Or maybe even a 2-second time step in Fathom XTS? Yes, you still can. You can do whatever you want with the time step. It's going to make your XTS model run a lot longer, and it's just going to give you more resolution. But keep in mind, no matter how small you make that time step in Fathom XTS, you're not going to be able to see what is shown right here. So this is surge analysis. And what I am showing right here is vapor volume on the right-hand side and pressure on the left-hand side. So let's break this down and let's look at things one thing at a time. So here is the static pressure at the outlet of the valve, okay? I'm sorry, outlet of the pipe. So this is right here, the outlet of pipe 5. That's the inlet of valve B, okay? So when we take a look at that, what is that increase in pressure? Well, remember from XTS, we saw that the pressure increase was 5 to 10 PSI. Not the case here. We're at 190 PSI. That gets up to right here about 435 PSIA. So that pressure spike is massive. Now, let me show you a really cool tool. This guy right here is called our rangefinder, which it's already turned on. The rangefinder allows you to zoom in to different points of the x-axis. So I can zoom in right here and see what's going on a lot easier. So I have right before the valve is closed. So remember, that valve is closing in 5 seconds. Look at this. Nothing happens for almost the first 5 seconds. What in the world is going on? Well, there's also an important thing to pay attention to with the type of valve and the type of system that it's installed in. This particular valve here, when I was closing it linearly in 5 seconds, this is not going to make an impact on flows, pressures, velocities in the system at all until the very last few open percentage values of the valve closure. So even though we're closing this in 5 seconds, nothing happens until maybe 4.9 seconds. So keep that in mind, where you may think, well, I'll just close my valve over a longer period of time. Well, that doesn't always do it. Now, will you have a smaller spike right here than if you close the valve in 3 seconds? Probably. And actually, I already did that analysis for you. Here's a 3-second valve closure I did for fun. So if I plot that scenario with this, another question was, can you change units to pressure as gauge? Absolutely. All you would do is click on the drop-down menus, and that's where you can change your units. So no problem there. Another question I got is the data from the graphs easy to export to Excel? And the answer is yes, it is. It's no trouble at all. You can either click on this button to copy the XY data and paste it into Excel manually, or you can also set up our Excel export manager to copy and paste the results. Now, I'm not going to demonstrate that today, but here, let me turn off a lot of these parameters so we can focus on what's going on. So here's the one of the closures, and then let's see, where did it go? Oh, that's vapor volume. Let's see. Ah, here's the scenario I was looking for. Okay, so the light blue, this is the pressure at the inlet of the valve, valve B. If I was closing the valve in 3 seconds then instead of 5 seconds. So you do see that in a 3-second closure, you do have a higher pressure spike than in a 5-second closure. But the response is virtually the same. So nothing happens until that last little bit of valve closure. So again, It's not just about closing over a long period of time. It's about how you close your valves. All right. So this just goes to show the pressure surge that's going on. You can look at your pump flow rate, and you can see how your pump changes. So right when that valve closes, you have a sudden surge that your pump experiences as well. That's not something that Fathom XTS is going to be able to capture. Now, one other type of plot that you want to do is maybe a profile plot, where I've already created these flow paths, a path through valve A, through valve B, and through valve C, and you'd want to take a look and see how the pressure changes along those flow paths. So here is where I have my profile plots. Let me change this up a little bit here. 2500, 250. There we go. And so when you play the animation, this will tell you what's happening over time. And as you can see here from that valve closure, nothing really happens until the very last few open percents. Okay, so look at this time spot. It's at 4.8 seconds, okay? So nothing is going on in the system, no decreases in flow or anything like that until the valve is almost all the way closed. So now that that's at that time step, let me slow down the graph a little bit, and we can see how the valve closure in valve B will impact the pressures that the other two flow paths will see. This is why waterhammer analysis is really important, because as we have this surge that's passing through the system, you're going to see an associated pressure surge in the other two flow paths. That wave is going to travel down, and it's going to reflect off the discharge reservoirs, and then it's going to travel backwards, and all those waves are going to interact with each other, and you might start to see cavitation in these other systems, and that could be a problem, even in a very simple system like this. So those waves are traveling down, and then the red one, that reflects off the valve or the tank A, and you can see how that wave front travels back, and we start to have an interaction, and you can see the following wave here traveling back, and all these are going to interact with each other, as you can see, and this will bring about some very interesting transient responses. And look, this is all within 6 seconds of when that valve starts to close. None of this is captured in the AFT Fathom XTS module. This is why it's really important to do your impulse analysis for waterhammer as well. So that's what the flow path looks like, and those are some things that you would look at. Just to show really quick, here's how you can generate a graph from the workspace. Right click on a pipe or a junction. You can do transient graphs for junctions like pump speed, head rise, pump power, or you can do, the transient graphs for the connected pipes. So maybe I want to show flow rate for the connected pipes. This will be the flow through the pump, and once this plots, here you'll see what that looks like. There we go. And so that's the flow rate through the pump. Now, I'm not really going to demonstrate these last scenarios because you would basically look at the same types of results. You would look at pressures at the valves, flows through the pump. You would maybe look at the DP across your pump just to monitor that to see if you have any problems. Analyze for cavitation, do your profile plots and your animations to see how things are changing all throughout the system at different points in time. But I want to walk you through how to set up the scenarios. So here, this is the second scenario when valve C closes. So if you remember from the XTS module, when valve C closes, this valve is already closed. That's why the dotted lines are there, is because it shows that we've already closed off the flow. So how do we model the situation where we're trying to do a valve closure at valve C when valve B is already closed? And here's a very simple way to do it, is by replacing valve B with a dead end junction. If you wanted to, you could still keep the valve there and then have your downstream pipe with your reservoir, but that's not necessary because I didn't care about what's going on in this path here once this valve is closed. Nothing's going on because that's just going to settle out eventually. So to simplify the model for myself, I replaced the closed valve with a dead end. And so now, here's what's going to happen. When this valve closes, you're going to see that high pressure surge propagate down through this path right here, and then it splits. It's going to split up in this direction, and it's going to continue down, and it's going to split back towards the pump and split up this direction. Well, this is a reflecting point. So that's going to reflect a wave back, which is then going to split off in two different directions, while your initial waves are still traveling to their associated reflecting points, and then they will reflect back accordingly. And so as you can see, there's a lot of madness that's going on. This is another reason why it's really important to do your waterhammer analysis and your surge analysis, because you can very clearly see that if you close the valve here, it's going to make an impact all in the whole rest of the system. And that impact may be severe and cause lots of damage. You don't know until you look at it. And so we can get an indication by looking at the pressures in these pipes. So just really quickly, I selected those pipes on the workspace, and I'm going to right click and I'm going to do a transient graph for the pipes for their pressure only at the outlet. I don't really care about the inlet. I'm just going to show the outlet of the pipes right at the valve inlet. And so here we can see that there's a lot more going on. So when I turn on my rangefinder and I zoom in, you can see what's going on here. So this is the path where the pressure, so this is the valve C closure. And then here's the pressure response that you see when that wave has propagated to the other two valves in the system. And so you can see how that impacts other areas even when we're closing that valve several thousand feet away. And then here's the last scenario. I named it very carefully. Valve A closure, B and C already closed at 187 minutes. So remember, I'm still needing to make sure I specify the liquid heights correctly at that particular time step from the Fathom XTS scenario. But here I simplified things. Here's a dead end and here's another dead end. And once this valve is closed, we can see what's going to happen when this pump starts to deadhead. So if I do a plot for the pump flow, what in the world is going on here? Why do we see this crazy behavior? Well, what's really going on is when we zoom way in to just a very small range, this is massive pump oscillation, okay? You can see how that flow is oscillating back and forth through the pump very, very quickly. Several problems here. One, we have reverse flow to the pump. What's the pump head? This is where we need a 4-quadrant data set. I'm not going to talk about that right now, but that's something that you would consider next. And we're going to be deadheading against those closed valves. We don't want to happen, or we don't want that to happen. So the next thing that I would do is I would do a scenario where my valve A closes and I'm tripping the pump. That way I avoid deadheading at the pump, and that's the next thing that I would look at. All right, so hopefully that gives you a really good taste of when you would use the AFT Fathom XTS module. Again, that is modeling long transient simulations, and every time step is a steady state solution. And keep that in mind, it is not accounting for the wave speed of the fluid in any way. It's missing all that information. Impulse you need for doing a water hammer or surge analysis, that is for sudden transients. So in Fathom, we wanted to know how long it takes the tanks to fill up, what times do the valves close, and was I, criteria satisfied. Impulse, we take that information, we look at, okay, we know that the valve is going to close at that time step. Let's see what happens exactly when the valve closes and several seconds after. Are we going to have a surge pressure problem anywhere? Keep in mind, large pressures, low pressures are just as bad as high pressures, because if you get below atmospheric pressures in your pipes, you can have pipe collapse, and that brings on a whole new set of problems, especially if you're cavitating, and that's all stuff that you need to look at with AFT Impulse. Let's see, one other question somebody asked, can you color code the, well, we don't ever use the word node in our software. That's not what we use. We don't have nodes. Impulse uses stations, which are in the pipes themselves. And so these stations are the calculation points for the method of characteristics. And you can color code them with using the visual report. So here's the cool feature, is on the visual report, I can animate, using the visual report, it's not very helpful for Impulse, because I mean, you can do maximum and minimum pressure, but it's not very useful because your graphs are going to be your best friend. But here's what you can show is an animation of the pressure throughout the system. And so here's what this does. You can see how the colors change as the waves propagate. So let me speed this up. So remember, this valve is closing right here, and nothing happens until right when the valve closes, and your higher pressure is going to be yellow and red. So that's what we're looking for. And so this is going forward in time. Let me see, where's my time? There it is. So right about now, this is when you start to see that rapid propagation. And so if I back this up here and slow it down, this is really helpful for illustrating how those pressure waves interact with each other. So you can see what's going on. And when you see the very dark blue, that's where you might have really bad issues with cavitation and high pressures that are trapped in this area. So that's how you would be able to color code things, not really at the junctions, but in the pipes themselves. And then one last question, can you show the pressure and flow to the other flow paths when valve B is closed? I'm going to refer you back to my blog on that. If you have Impulse, this is a study that you can also do on your own. If you have Fathom and Impulse, or you can also download the free viewer. So if you want to go to downloads, free viewers, you can download these and then send me an email, benkeiser@aft.com, BENKEISER@aft.com. I'll be happy to send you the models. That way, if you don't have Fathom or Impulse, you would at least be able to look at the results with the viewers. They are very limited, but you can at least get something. And then I do document really well the results in the blog that I wrote. So again, go to our tips and tricks page and then just do a search for transient, and you'll find, well, right now it's easier to find it because, live it's pretty close, but it's called What is Transient Analysis? And this is where you can see a lot of the other graphs that I've provided. All right, thank you everybody very much for your time, for listening in today. Let us know if you have any questions, and if you want to try out Fathom's XTS module or AFT Impulse. If you're in the United States, contact me, benkeiser@aft.com. If you're outside the United States, feel free to contact your local channel partner, which you can find on the channel partners menu, channel partner locations, and they'll be able to help you accordingly. All right, take care everyone, and have a wonderful rest of your day and week.